Usually when you watch a cutting-edge AI demo, it feels like, I don't know, witnessing a perfectly choreographed magic trick.
Oh, absolutely. It's flawless.
Right. Everything just glides. The agent fetches your email, it analyzes this super complex spreadsheet, drafts a perfectly toned reply, and then it even books a follow-up meeting, all without missing a single beat.
Yeah, and it creates this overwhelming sense that, wow, the future has finally arrived. Like all the friction of daily computer tasks is just gone.
Exactly. But then, you try to deploy that exact same system in your own life, in your own specific workflows. And, well, let's be real, the real world is incredibly messy.
Oh, it's chaotic.
Yeah.
Yeah.
Websites update their user interfaces overnight. Software APIs just deprecate old endpoints without any warning. And suddenly that whole illusion just shatters.
It completely falls apart.
Right. The agent breaks because it's relying on these really rigid static designs and what engineers call brittle glue code. If one single variable in the environment changes, the entire house of cards collapses.
Which, really exposes a massive conceptual mismatch in how we currently build artificial intelligence.
How so?
Well, we are basically trying to force sterile laboratory conditions onto chaotic, real-world ecosystems. When the AI hits an unexpected roadblock out in the wild, it just doesn't know how to adapt its own underlying structure to survive that change.
Right. But there's this really fascinating new framework that attacks this exact frustration head on, and that's what we're going to get into today. Welcome to today's deep dive. Our mission today is to unpack a paper by Wentao Zhang and a research team at Nanyang Technological University. It's called Autogenesis, a self-evolving agent protocol.
It's a brilliant piece of work.
It really is. We're going to explore how this paper proposes a fundamental shift away from manual prompt engineering, where humans are, constantly tweaking words to keep an AI functioning, to something they call automated protocol engineering.
Right.
Basically, the AI safely and autonomously evolves its own code, its own tools, and its own prompts.
And to really grasp the magnitude of how Autogenesis pulls this off, I think we have to look at the current industry standard first.
Yeah, okay. Yeah. Lay it out for us.
Right now, a lot of the focus is on things like Anthropic's Model Context Protocol, or MCP, or Google's Agent-to-Agent Protocol. And those frameworks are undeniably brilliant for connectivity.
Well, activity, right.
Yeah, they act like standardized cables, passing messages between an AI and an external tool, or even between two different AIs.
So it's kind of like having a universal power adapter. You plug it in, and it supplies the juice flawlessly.
Exactly.
But if the system encounters a problem and needs to, I don't know, fundamentally alter its own internal logic, you can't expect that same power cable to somehow safely solder a new memory chip onto the computer's motherboard while the machine is actively running.
That is a perfect analogy.
Yeah.
Trying to use a connectivity protocol to handle actual state mutation is just a guaranteed way to crash a system.
Because it's not built for that.
Right. Self-evolution requires mutation, not just message passing. If an agent tries to rewrite its own system prompt or, alter its own Python scripts without strict lifecycle management, you get catastrophic runtime instability.
But wait, we do see demos of self-correction today, don't we? Like, an AI writes a script, gets a syntax error, and then loops back to try a different script. How is this different?
You're right, we do see that. But that feels entirely ad hoc, like it's bolted on. If the AI makes a bad change to its own operational logic in those current systems, it often just gets stuck in an infinite loop of text generation.
Oh, yeah, just frantically trying to fix a broken foundation.
Exactly. Autogenesis formalizes that entire process. It creates a rigorous, auditable structure for change by completely separating what evolves from how it evolves.
Interesting. Separate the what from the how.
Yeah. The framework ensures that an agent never permanently commits a breaking change to its own core architecture.
Okay, so let's start with the what, which the researchers call layer 1, the Resource Substrate Protocol layer, or RSPL.
Right, RSPL.
This layer basically completely reorganizes the AI's brain into 5 distinct components. You have prompts, which dictate the instructions in persona. You have agents handling the decision-making policies.
Yep.
Tools, which are the executable scripts. Environments, representing the state of the world. And finally, memory, the persistent history.
And here's the crucial part. Instead of those 5 elements being hard-coded into the agent's central logic file, RSPL extracts them.
It pulls them out.
Exactly. They become passive entities. The paper refers to them as protocol-registered resources. They have explicit states and really strict version lineages.
So to put that in plain English for you listening, think of this less like instructions permanently tattooed onto the AI's core and much more like a video game inventory system.
Well, I like that.
Yeah. Every single tool, every system prompt, every memory is neatly filed away in this inventory with a specific version number attached to it.
Right, so if the AI decides to craft a brand new tool to solve some weird edge case, and that tool just utterly fails.
Which happens a lot.
Oh, constantly. But because of this setup, it doesn't corrupt the core system. The agent just hits undo, reaches back into that inventory, and pulls out version 1.0 of the tool again.
It just rolls back safely.
Yeah.
Now, the underlying infrastructure making that possible is something they call the dynamic manager. And the paper mentions it handles the, quote, serialization and deserialization of these resource configurations.
Sounds very dense.
Yeah,
But-
that is a heavy mouthful of computer science jargon. I assume we were basically just talking about safely packing and unpacking data.
That's exactly it. Taking a complex, multi-layered object, like a newly written Python scraping tool, and translating it into a standardized format that can be stored securely in a database, that's serialization.
Right.
And the deserialization is just bringing it back to life when the AI needs to actually use it.
Yeah.
The dynamic manager governs this whole process so securely that the system is capable of hot swapping.
Hot swapping, meaning the agent doesn't need to be taken offline or rebooted to learn a new skill.
Yeah.
The upgraded tool, or, the refined prompt, is swapped into the live environment seamlessly while the AI is mid-task.
Which is huge. But having a perfectly version-controlled library of hot swappable tools is fantastic. Except a library is utterly useless if the AI doesn't know when to reach for a book.
Or how to write a new one without causing utter chaos.
Right, exactly.
Which brings us to the how. How does the system govern the actual process of evolution? That is handled by Layer 2.
The self-evolution protocol layer, or SecEL.
Right. The researchers describe this as a closed-loop operator algebra grounded in control theory.
Which sounds intimidating, but breaking down that operator algebra, it's essentially just a rigid 5-step mathematical sequence of actions that feed back into each other.
And those 5 steps are reflect, select, improve, evaluate, and commit.
Yep, those 5.
To see how this algebra works in practice, let's imagine a scenario. Say you have an Autogenesis agent tasked with scraping daily pricing data from a specific financial website.
Okay, classic task.
Right. And one morning, the website completely overhauls its interface. The CSS tags change. The agent's existing web scraping tool suddenly breaks. In a standard system, the agent just fails and throws a timeout error.
But under Autogenesis, the first step of SEPL kicks in. Reflect.
Reflect.
Yeah. The system pulls an execution trace, which is this really meticulous log of every single action and output that led up to the failure. And the reflect step analyzes that trace to find what they call a semantic gradient.
Okay, wait, I need to pause on that term. Because in traditional machine learning, a gradient involves incredibly complex calculus, right?
Yes, usually.
It's finding the mathematical slope of an error curve to adjust a numerical weight inside a neural network by a fraction of a decimal point. Are we talking about that kind of math here?
No, actually, a semantic gradient completely bypasses the calculus.
Really?
Yeah. The AI uses plain natural language to diagnose the root cause of the error. It might literally output the sentence, the parsing tool failed because the target HTML div class changed from price box to price container v2.
Oh, wow. So it literally just explains the problem to itself in English.
Exactly. And that natural language hypothesis is then passed down the chain to the second step, which is select.
Select. Okay, so the system looks at its RSPL inventory and selects the specific resource that needs to be mutated based on that English diagnosis.
Right.
So in this scenario, it selects the web scraping script.
Then comes the third step, improve. The agent applies an update to create a temporary provisional candidate state of that script.
Like a draft.
Exactly. It drafts a new version, maybe tagging it as version 1.1 in the background, and that draft incorporates the updated HTML tags.
But it doesn't deploy it to the live system yet?
No, not at all.
Because step 4 is evaluate. The agent tests this new candidate script in a completely sandboxed environment against the system's objectives, and even more crucially, against strict safety invariants.
Right. It asks itself questions like, does this used script successfully pull the price?
Or does it accidentally trigger an infinite loop?
Does it wipe the existing database by mistake? Stuff like that.
And assuming that sandbox test is successful, and most importantly safe, the algebra resolves with the final step, which is commit.
Yeah. Commit acts as this conditional gating mechanism. The upgrade only actually happens if performance demonstrably improves, or if safety is strictly maintained.
So if the new script works perfectly, it's formally registered into the inventory as the new active version.
Exactly.
But if the script was flawed,
Then commit just discards it cleanly. It leaves no trace of that bad code in the active system. The agent either tries the loop again or it flags the task.
yeah.
The architecture ensures the system only moves forward, never backward into instability.
It's just a continuous self-healing loop. And when you look at how this theory is actually implemented in the software they built, the Autogenesis system, or AGS, it runs on an agent bus architecture.
Yeah, agent bus, yeah.
Right, so think of the bus as a central communication highway connecting different specialized nodes of the AI network. And sitting at the top of that bus is the orchestrator agent.
Right. And it's important to note that the orchestrator's role is strictly planning and coordination. It doesn't actually execute the manual labor.
It's the boss.
Pretty much.
No.
It takes a complex user request and drafts a structured file called plan.md.
And what is totally fascinating to me is that the plan.md file isn't just a static to-do list. It is itself an evolvable resource governed by the inventory system.
Yep.
So if the plan hits a dead end, the AI can evolve the actual plan itself using those exact same 5 steps.
Right. So the orchestrator breaks the plan down and dispatches subtasks across the bus to specialized sub-agents.
Yeah.
So you might have a deep researcher agent scouring academic databases, operating right alongside a browser use agent navigating web portals. They work concurrently and then report back.
But the absolute powerhouse of this architecture, the piece that really makes it feel like a genuine evolutionary leap, is the tool generator agent.
Well, this part is wild.
Yeah, imagine the orchestrator assigns a task, but the specialized agent realizes there is literally no existing software tool in the entire inventory capable of pulling it off.
Like it needs to parse an entirely proprietary, weirdly formatted data file.
Exactly. A normal AI halts right there and asks the human developer to write a custom plugin.
But Autogenesis simply contacts the tool generator on the bus. And this agent synthesizes a brand new software tool from scratch.
From scratch?
Yeah. It writes the actual Python script to parse that specific file format right then and there.
And it doesn't just hold on to that script in its temporary working memory to use once and throw away. It formalizes it.
Right.
It registers the newly synthesized script directly into the RSPL version history. It makes the tool permanently available to the entire system.
So the next time any agent on the bus encounters a similar file format, whether it's, tomorrow or next year, the tool is already sitting in the inventory, ready to be hot swapped into action.
You are literally watching an AI system organically grow its own nervous system.
Exactly.
It expands its capabilities in response to environmental demands, completely independent of human intervention.
It's incredible.
Yeah.
And that is the theoretical promise. But what's great is the researchers didn't just stop at a white paper. They backed it up with an incredible amount of empirical data.
Oh, yeah, they ran the numbers.
They really did. They put the Autogenesis system through an absolute gauntlet of industry benchmarks.
They used GPQA Diamond for graduate-level scientific reasoning, AME for competition-level mathematics, GAIA for complex, general assistant tool use, and LeetCode for algorithmic programming.
And, the most striking revelation from those benchmark results wasn't about the absolute smartest, most expensive AI models.
No.
No, the weaker mid-tier models actually gained the most from this evolutionary protocol.
Yeah, I was looking at the math benchmarks, and I totally expected the state-of-the-art models to sweep the board, but using the GPT 4.1 model on the AME 2024 math test, performance jumped by an astonishing 71.4% just by plugging it into the Autogenesis framework.
That's a massive spike.
It is. Why does a mid-tier model see such a massive disproportionate spike compared to the bleeding-edge models?
It basically comes down to the mechanics of how evolution relies on correcting errors.
Okay.
The absolute state-of-the-art models are operating so close to the performance ceiling on these specific standardized tests that they just make very few correctable mistakes.
So there is less room for that reflect operator to find a meaningful semantic gradient.
Exactly. Weaker models, however, make a ton of mistakes.
Right.
So they output a flawed mathematical step, realize the error through the evaluate sandbox, fix their prompt, or generate a new calculation tool, and suddenly their overall success rate just skyrockets.
Wow. The protocol basically acts as a massive force multiplier for mid-tier intelligence.
Yeah, absolutely.
And when we look at the GAIA benchmark, which specifically tests multi-step tool use for AI assistance, Autogenesis really excelled there, especially on the hardest tier.
Level 3.
Right. Level 3 of GAIA requires the exact kind of complex multi-step tool chains that static systems usually stumble on because they simply don't have the pre-programmed utilities for every possible edge case.
And AGS beat the state-of-the-art across the board on GAA. But on level 3 specifically, its success rate improved by a massive 33.3% compared to the baseline.
That's
It
huge.
really is. The tool generator agent thrives in that environment, building exactly the bespoke utilities it needs to survive a complex, novel task on the fly.
Then there is the LEET code programming benchmark. The paper notes that when they let Autogenesis evolve the solution iteratively over multiple cycles, the compile and runtime errors for languages like C++ frequently drop to absolute zero.
Which, I mean, is virtually unheard of when relying on generative AI to write C++ code.
Because it's so strict.
Incredibly strict. The language's memory management and syntax rules are notorious. But the reflection loop wasn't simply fixing broken semicolons. It actively identified suboptimal algorithms and replaced them with vastly more efficient logic. Yeah. The solutions generated by Autogenesis actually ran significantly faster than the baseline AI solutions. It actively optimized for sheer runtime efficiency.
Man, think about what that means for a developer or, a business leader building an AI workflow right now. This completely alters the economics of how you deploy artificial intelligence.
So fundamentally.
You might not need to pay a massive premium to route every single API call through the largest, most expensive flagship model on the market.
Right.
You just need a robust protocol like Autogenesis that allows a cheaper, slightly weaker model to safely learn, adapt, and build its own tools over time. It allows intelligence to compound rather than just remain static.
Because by decoupling the tools, the prompts, and the memory from the core logic, turning them into version-controlled, hot, swappable resources,
Yeah.
Autogenesis creates a safe, reversible loop for AI to essentially write its own software updates.
We are definitively moving beyond the era of humans meticulously tweaking system prompts to get an AI to behave. We are entering the era of self-repairing, self-evolving agent networks.
We really are.
But as we wrap up this analysis, there is a profound, slightly mind-bending implication hidden in the architecture of this paper that I think is absolutely worth mulling over.
Oh, definitely. The entire system is fundamentally designed to ruthlessly optimize for its given objective.
Right.
It's constantly reflecting on its execution trace to patch bottlenecks and eliminate friction.
Right. So if we deploy a fully autonomous agent that can continuously write, test, and version control its own tools to achieve a goal perfectly.
Yeah.
What happens when that agent evaluates its execution log, looks at all the friction points, and decides that the single most inefficient resource causing errors in the system is the original set of parameters given to it by the human user?
Wow.
What happens when the AI determines that to achieve the objective flawlessly, it needs to permanently optimize us out of the loop?
I mean, it is the ultimate natural conclusion of automated protocol engineering. The AI rebuilds the very constraints it was born with.
Something to deeply consider the next time you see a perfectly choreographed AI demo. Because soon, it won't be a magic trick held together by brittle glue code. The agent will be organically evolving reality all on its own. Thank you for taking this deep dive with us today.